Okay, we're going to look at this next example where 32% of all college majors are STEM majors, and we're going to select 42 students. 42 students are randomly selected, and we have to find the probability of these various cases, 4 different cases. Now in Part A, we want the probability that exactly 11 of the students selected are STEM majors. So the random variable here, x, is counting the number of STEM majors. And since there are 42 students selected, the random variable can be any of the numbers between 0 and 42. So in Part A, we want the probability exactly 11 of them are STEM majors. So in Part A, we want the probability that x is equal to 11. And that's like the case we had done before, where this is a binomial scenario because each student constitutes a binomial trial, and there's either success or failure. Success is being a STEM major, failure is not being a STEM major. There's 42 different trials. Again, each student constitutes a trial. They're independent. The probabilities are same from trial to trial. So this is a, the binomial distribution does apply here. So if we want the probability x is equal to 11, we can calculate this as there's 42, n is 42, so of the 42, choose 11. Success occurs, the probability of success in a single trial is 0.32 because 32% of the students are STEM majors. So that means P, which is the probability of success, is 0.32. So success occurs 11 times, and failure, which is 1 minus 0.32, is 42 minus 11 times. So what is that? We can do that calculation using the binomial PDF. And the syntax there is n, which in this case is 42. P is 0.32. And the value of interest here is 11. So if we go to distributions, which is second vars, and we have to scroll all the way down up to 0 colon. N here is 42. P is 0.32, and the value of interest is 11. So to the 4th digit, it would be 0.0991, because if we round to 4 decimal places, this one is larger than 5, so we have to round up. So it'll be 0.0991. This is approximate. Okay, in Part B, we want the probability at most 13 of them are STEM majors. So at most 13 is an inequality. We want the probability at most 13 is 13 or fewer. So we want the probability x is less than or equal to 13. The probability x is less than or equal to 13, well, that's why I have put this already here for you to take a look at. If you want the probability x is less than or equal to some particular value, that's going to be equal to the probability that the random variable takes on all the values less than or equal to the one specified. So that would be the probability x is equal to 0 plus probability x is equal to 1 plus probability all the way up to, in this case, x is equal to 13. So since we have the sum of these probabilities, we can do that calculation. We could use the binomial PDF 14 times and add them all up. Or alternatively, we could use the CDF. The CDF, C here stands for cumulative. So this is the binomial cumulative distribution. And the cumulative distribution is the sum of these probabilities. It's a sum. So it's a cumulative distribution. So again, the probability x is less than or equal to 13, that's going to be equal to probability x is equal to 0 plus probability x is equal to 1 plus all the way up to 13. And we can calculate that using the binomial CDF. And the syntax for that, n here is still 42. P is still 0.32. And then the k in this case is the upper bound. The upper bound here is 13. So if we go back to distributions, underneath the PDF is the CDF, the cumulative distribution function. And if we use this one, again, number of trials is 42, probability of success in a trial is 0.32, but now the upper bound is 13. So to 4 decimal places, this would be 0.5159. So this is about 0.5159. Okay, now part C, the probability at least 12 of the students selected are STEM majors. Okay, so at least 12 is, at least 12, how would you rate that as an inequality? That's going to be the probability x is, at least 12 is the same as 12 or more. So that would be x bigger than or equal to 12. X bigger than or equal to 12. Well, that would be probability x is equal to 12 plus probability x is equal to 13 plus all the way up to 42. So we could add those up, but it would be a nuisance to do that. Alternatively, we could use the complement, and that's the thing that we would do in this case, because rather than add the probabilities from 12 to 42, which is an awful lot of times to use the binomial PDF, rather than do that, we can use complement and use the CDF. Now, bear in mind, the cumulative distribution function starts at 0. It starts at 0. So, but the thing to notice is, here, let me get a different color. The thing to notice is we want the probability x is bigger than or equal to 12. So here's the values for x, right? And if x is bigger than or equal to 12, this is the event that we're interested in. This is our event, E. But E, we know about complements already. And the complement of our event E is x takes on the values 0 through 11. So this set here is E complement. And we know E and E complement, the probability of E plus the probability of E complement adds up to 1. So we're going to make use of that fact. And to do this calculation, this will be equal to 1 minus the probability that x is less than or equal to 11, which is the complementary event. And that's going to be 1 minus. Now we can use the binomial CDF to do the probability x is less than or equal to 11. So that will be 1 minus the binomial CDF. And again, the syntax is n, which is 42. I'm going to run out of space here. P, which is 0.32. And the upper bound of interest here is 11. Okay, so what is that? That's going to be equal to, so if I come over here and actually, nope, I don't want that. I want 1 minus the CDF, the binomial CDF, n is 42, p is 0.32, and the upper bound in this case is 11. So that calculation yields to 4 decimal places 0.3753. I said 3753, but I said the wrong thing. I should have said 7353. Okay, and now in this last case, what's the probability between 9 and 17, including 9 and 17 of them major in STEM? Okay, so in this case, we want the probability that X is between 9 and 17. Okay, well, again, we want to find a way to use the cumulative distribution function, and it should be clear to you that this is going to be, the CDF up to 17, subtract the CDF up to 8, because we need to include, 9 is a possible value for X, so we can't subtract that. So that's going to be the, oh, that's my phone buzzing. Binomial CDF, N is 42. Probability of success is still 0.32, but the upper bound here is 17. So that's going to add all the probabilities from 0 to 17, but we want to subtract from those the binomial CDF. We want to subtract 0 through 8. So subtract up to 8. And that will give us the values from 9 to 17. Because again, this second piece will subtract the values X takes on 0, so 0 through 8. Okay, so if I do 42.32 and 17, and then subtract from that (42, 0.32, up to 8), then I will have the values between 9 and 17, and if I round to the 4th digit, it would be 0.8617, because in the 5th digit it's bigger than 5, so we have to round up. So this would be approximately 0.8617.